Today, we're going to talk about tiling and tessellations. You've probably, I know you have, seen floors made out of squares or rectangles or triangles or hexagons. That's tiling, and those are tessellations. There's several numerical sequences and number patterns that are used in art and architecture, such as triangular and square numbers. Once we develop an understanding of the basic notions, we'll transition into how number theory is used to create works of art within a given architecture. A tessellation, or tiling, is the covering of a plane with a repeated geometric pattern with no gaps or overlaps. Before we get into tessellations and tiling too much, we need some introduction here. Triangular numbers refer to numbers such as 1, 3, 6, 10, 15, where the number represents the number of objects that can be arranged in a triangular manner. So you could have 3 dots to make a triangle, 6 dots could make a triangle, 10 dots could make a triangle, 15 dots could make a triangle, and so forth. The pattern of triangular numbers is this. The first one is just 1. The second is 3, which is 1 plus 2. The third is 6, which is 1 plus 2 plus 3. You add up all the previous. Then 1 plus 2 plus 3 plus 1 plus 2 plus 1 is 10. And that makes each time you add the previous. Find the 27th triangular number. We do have a formula for that, which we'll look at in a minute. I'm going to go ahead and give it to you because it's going to make this a lot easier. The formula, for a triangular number is T sub n equals n times n plus 1 divided by 2. So T sub 27 would be 27, this is the 27th number, times 27 plus 1 divided by 2, or 378. That's the 27th triangular number. There'd be 378 dots making that triangle. Back to Pascal's triangle. In Pascal's triangle, if you look at the third diagonal row from the right, you see the triangular numbers. Square numbers. Well, they make a square. So 1 and then 4, 9, 16, 25. Probably see the pattern already that they're the number or the length of the side squared. Here, the square numbers, they're not there. Well, here's how they go. 4, 16, 25. I think I got ahead of myself. Okay, 4, 9, 16, 25, 36. It keeps going from there. The formula to find the nth square number is just n squared. Look at these triangles. This is also Pascal's triangle. Consider the first two triangular numbers, 2 and 3. The sum of the two triangular numbers is 4, which is a perfect square. This pattern actually continues for every pair of consecutive triangular numbers. Their sum is a perfect square. So if you've got this first picture where you've just got one triangle, it's 1. Okay. But if you take the midpoints and draw another triangle, you get 4. If you take the midpoints of that or the 1/3 waypoints and draw triangles, then it's 9. If you draw every quarter of the way on the sides, you get 16, and every fifth, you get 25. And depending on how many triangles are at the base is what you get. So there's 2 on the base there. 2 squared is 4. There's 1, 2, 3 here. 3 squared is 9. 1, 2, 3, 4 squared is 16. 2, 3, 4, 5 squared is 25. And it makes the pattern of n squared. How many total triangles are in this triangle? And now, it's not talking about overlapping or anything like that. So it's not one of those you see on social media. How many triangles are there? There'd be a whole lot. But how many are actually drawn that you can see? Well, you could count them up, or you could say at the base there's 1, 2, 3, 4, 5, 6. And 6 squared is 36. There's 36 of the small triangles in this picture. Let's look at Pascal's triangle for a second. You can get this pattern just by connecting the numbers. Okay. A regular tiling or tessellation uses shapes that are regular polygons. So regular polygons meaning a square, an equilateral triangle, a hexagon where all the sides are the same. The process of tiling or tessellating a plane hinges on the key fact that the sum of the interior angles of the geometric figure at a common vertex must be 360. So if we look at this vertex, all the way around, these angles would have to be 360 for a tessellation to work. Here, if you add that one, 360. Here, if you add these 3 angles, it'll be 360. In order to be able to tessellate, that has to happen. Here are some different ways that you could do a translation or tessellation. A translation is a motion in where an object is moved by sliding. So you could go to the right, left, up or down, diagonally. That's a translation. Rotation, it's just rotating the object. So this one was rotated clockwise 80 degrees. And reflection, it's reflected about some line. Translations, rotations, and reflections can be classified as rigid motions. That means that the motion itself does not distort the object's size or shape. It's not making it bigger or smaller, it's just moving it. In order to create a perspective drawing, Troy wishes to translate the following figure to create a 3-dimensional drawing. Translate the figure 10 units to the right and 2 up. So we would take each vertex and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. right there. I'm going to mark that and come back to it. Okay. And then this one, 10 spaces, would be right there, I believe. And then this one, 10 spaces, would be right here. Let's make this a little bigger. We're also going up, though, so we've got to move this one up, too. So there we go. I'll erase the old one. This one needs to go up, too. This one needs to go up, too. And then this one will come over 10 and up 2. And then at the top, we'll come over 10 and up 2. And so that makes our pentagon. And then if we connect, then it would make a three-dimensional figure, like a house. This one you wouldn't be able to see, so that's why I'm doing it diagonal or dashed. So there would be our three-dimensional figure. Oh, there it was bigger. Regular tilings are tilings where the tiles are all the same and are made up of polygons such as equilateral triangles, squares, regular pentagons, or regular hexagons, etc. Archimedean tilings are regular tilings that are composed of multiple regular polygons. Like here we have a regular hexagon, a regular square, or a square, and an equilateral triangle. And they fill the surface. Again, at any vertex, all these angles have to add up to be 360. The sum of the angles in an Archimedean tiling, well, it's kind of got a little proof here for you, but basically it ends up to be this here, where 1 over n sub 1 plus however many 1 over n sub 2 plus 1 over n sub 3, so forth, to however many there are, 1 over n sub k, is equal to k over 2 minus 1. It says if an unknown number of polygons, say k polygons, with a number of sides equal to n sub 1, n sub 2, n sub 3, and so on, meet at a singular vertex, the sum of the angles must satisfy this equation in order for the Archimedean tiling to be a tessellation. Show that this given tiling is an Archimedean tiling. So we've got a hexagon and a triangle. So at any given vertex, we have 1, 2, 3, 4 shapes. So that means that K is 4. N sub 1, if this triangle here is, we call it 1, it has 3 sides. If we call this triangle 2, N sub 2 is also 3. This hexagon, if we call it 3, then N sub 3 would be 6 because it has 6 sides. And this one, N sub 4, would also be 6. So we want to see if our formula works. So we want to see if 1 over n sub 1 plus 1 over n sub 2 plus 1 over n sub 3 plus 1 over n sub 4 is equal to k over 2 minus 1. Let's see. 1 over 3 plus 1 over 3 plus 1 over 3. Oh, excuse me. 1 over 6 plus 1 over 6 is 2/3 plus 2/6. I'm running out of space. And 2/3 plus 2/6, well, that's 2/3 plus 1/3, 3/3, or 1. So let's see if k over 2 minus 1 would also be 1. So k over 2, k was 4. 4 over 2 is 2. And 2 minus 1 is, in fact, 1. So that can be an Archimedean tiling. And last, just a final definition. Irregular tilings, or irregular or non-regular, are tilings in which there's no restrictions on the polygons. So they could be some kind of weird shape used to tessellate other than the requirement that the sum of the angles at meeting vertices must be 360. It should be noted that since there's no restrictions on the polygons in terms of the number of sides and interior angle measure, there are an infinite number of such tessellations.